the V-22 Osprey, a revolutionary new aircraft, a stunning climax to aviation's first century. The Osprey will replace troop-carrying helicopters for the U.S. Marine Corps and Special Forces units. It lands and takes off like a helicopter, tilts its rotors, and flies like a fixed-wing turboprop.
And it's going to be one of those things that we've been waiting for so long that when it comes, it's going to revolutionize what we do.
The Osprey was conceived in failure. Desert One, the Carter administration's disastrous 1989 attempt to free American hostages from the embassy in Tehran. Helicopters carrying Special Forces troops lacked the necessary range. They had to make a hazardous refueling stop in the Iranian desert and were caught in a sandstorm. The Marine Corps' Deputy Chief of Staff for Aviation, Lieutenant General Terrence Dake.
Well, of course, that was a national type of mission that had a great deal of visibility, so it becomes a catalyst to say, if you can't do that sort of mission, what do you need in order to do so?
The Bell Boeing V-22 is the response to that need. It's twice as fast as a helicopter, has 3 times the payload and 5 times the range. Over $5 billion has gone into developing this extraordinary aircraft. The Marines are its most persistent advocates. They see it as a means of avoiding amphibious landings against well-defended beaches.
Of course, the early portions of an amphibious assault, you don't have anything ashore. The enemy is ashore. You are not. And that first minutes, hours, become very important because you must get your forces ashore and get them with enough combat power in numbers and supporting arms that the enemy cannot dislodge them. So in cases in the past where we did an amphibious assault, we usually come into a beachhead, we'd try to build up a shore on the beach. We think that in the 21st century, that's a flawed strategy. The Osprey is designed to carry 24 combat-loaded Marines. But once you finish that mission in that early part of the assault, then we turn to a cabin area which really can be filled up with a gross weight of 10,000 pounds of carrying capacity. So the Osprey allows us then not to stop at the beach. And we'll actually fly from the ship directly inland, perhaps as far as 100 miles from the shoreline, and find where we want to go, put our forces, and then with the Osprey as a resupply vehicle, it would make its assault and then turn into a logistics carrier to fortify those and to resupply the people who are out there. So we believe that the assaults of the future will not be one of attrition warfare where you battle it out like we did at Iwo Jima. We have to avoid those.
Another advantage to the Osprey, it can fly to any point on Earth.
We went to Desert Shield and Storm. We took a lot of helicopters. We took several squadrons of helicopters. We actually had to break them down, take the transmissions off, take the rotor heads off, put them into large airplanes, fly them all the way to Saudi Arabia, offload them, find a crane, build them back up, test the airplane to make sure we'd done that correctly. Took us weeks, literally, to get our helicopters in place.
The V-22, flying as a fixed-wing aircraft, can fly fast enough to refuel from jet tankers and is stable enough to endure the turbulence of their wake.
So with 2,100 nautical miles of range, the Osprey literally can self-deploy. It can go without any teardown all the way, in this case, in the example I just gave you, to Saudi Arabia. We would have been on the ground and within a very short period of time been prepared to go into combat operations. Huge advantage, and one in which we no longer need to tie up our strategic airlift in order just to get our helicopters into the area. And those are the kinds of military reasons and requirements that have driven us to the Osprey.
For all its complexity, pilots say this hybrid aircraft is easy to fly. Next. Patuxent River Naval Air Station in Maryland, home to sleek and familiar aircraft like the F-18 Navy fighter bomber. Home as well to the awkward-looking Osprey with its huge flailing rotors. The Osprey will never win a beauty contest, but it's a triumph of aeronautical engineering. Its tilt rotor technology, the result of 40 years of work. The 4 aircraft based at Patuxent are still undergoing testing by Marine Corps pilots. Test pilot Major Christopher Seymour says this unique aircraft poses unique problems for a test pilot.
It's not an airplane, it's not a helicopter, so as far as flight test goes, it had to be approached from a completely different aspect. You know, you can test it in some profiles as a helicopter with traditional helicopter test techniques, and then in other profiles in airplane mode, it had to be tested like an airplane. Some of the unique problems that have occurred are, you know, the flow field around an aircraft in airplane flight is much simpler to model and predict what's going to happen than a helicopter in slow speed flight because of the downwash effects around the fuselage and the airplane. Typically, this phase of the program right now, we're still developing the envelope for the EMD aircraft, the Engineering Manufacturing Development aircraft. So we go out at certain gross weights and perform a particular maneuver just to measure the stresses and the loads that the aircraft feels during that maneuver. And it's very weight and center of gravity dependent.
The power plant on the nose there, and it's still giving me steering to the left.
A typical flight will go for an hour, hour and a half, and then we'll have to come back in and refuel and reset the center of gravity. It's very structured. One test flight will typically cover anywhere from 30 to 40 data points, if we call them, points that need to be flown and collected at that particular condition. The sensors on the aircraft are measuring data digitally and bursting it down via high-frequency radio waves to the telemetry lab, which is located here on the base. There's a team of engineers in the telemetry lab watching critical parameters at the time to make sure that none of the limits have been exceeded.
All the telemetry engineers at Patuxent Air Station have received flight training, so they can put a pilot's interpretation to the squiggles on their data charts. Telemetry engineer Mike Myers.
The engineers get to find out what it's like to actually fly in the airplane and see what it's actually like to get out in the fleet, and the pilots get to see what the engineers do in their job.
Go ahead. Yeah. It's radio check. Loud and clear.
I'm a mechanical engineer by education. I have a degree in mechanical engineering, so it's been a while since I've been in the Marine Corps. I've been out of college for over 10 years now, but I think I can communicate with them well enough so that they understand me in their language, if you will. We understand the information that they're after, but we also understand how to fly the aircraft, so we kind of connect the two and say, okay, this is what we might be able to get as far as your data, the information you're after, but doing that particular maneuver is just not possible in an aircraft.
And you probably killed that record, so that's probably long enough for them.
Get a record off.
Working up the Osprey is a time-consuming process. The aircraft are pushed up a step at a time, and everyone is concerned with safety.
Well, the era of kick the tire like fire is all over. All these airplanes cost into the tens of millions of dollars, and a lot of them are prototype aircraft. And if we lose them, essentially the program could be over.
2 Ospreys have been destroyed in crashes. In one of them, 7 were killed. The aircraft flipped over and caught fire as it was landing at Quantico Marine Air Station. Investigators found mechanical failures and design faults. And the cost of the program has resulted in problems in budget-conscious Washington. But the program has survived. Experienced pilots are now being trained to operate this original and unusual aircraft. A lot of that learning involves setting the angle of the engine nacelles. General Dake found it a piece of cake.
I actually flew the Osprey last August. I went to a short ground school to learn the system. I was most impressed by the redundancies in the airplane because I'm a helicopter pilot by trade. We have a good simulator that I got several hours in the simulator. But when I got in that airplane, it seemed to me it was a natural. We took off like a helicopter, lifted up into a hover. And within 5,000 feet of runway, we were at over 200 miles an hour. And for a helicopter pilot, that was impressive. And of course, we're into envelope expansion testing on that aircraft, so they asked that I stay below 250 knots. That airplane wants to fly. It did not want to stay below 250 knots. I was able to maneuver it quickly and easily. It reacted well to the controls. It was just a good aircraft from a pilot's point of view, very responsive. I'd like to go fly it again.
General Dake and every other pilot who takes the controls of an Osprey must put in hours in a simulator. It provides a remarkably accurate simulation of the aircraft's flight characteristics.
The training simulators will be pretty high fidelity, upwards of 80 to 90% fidelity, including vibrations, motion-based, full visual system, and I think that roughly 60% of the initial pilot training will be done in a simulator, which is a tremendous program as far as training requirements go.
A key difference in the aircraft's instrument panel, a display showing engine angle.
I have the nacelle angle set the way I want it, and I'm ready for a stow takeoff. I release the brake, and I add power, and I control my direction over the ground at slow speed with my pedals, just like in a conventional aircraft. And then when I'm ready to fly, I just add a lot of power, and it flies right off the ground.
When operational, Ospreys will spend much of their time aloft in a mode of flight that is half helicopter, half fixed wing.
Comfortably, I can stay, 100 to 120 knots at 60 nacelle. This would probably be where we're going to do most of what you consider conventional helicopter work at 60 nacelle and 110 knots.
Helicopter pilots marvel at the Osprey's ability to head toward a runway at 230 miles an hour, then quickly shift into a hover for landing.
Okay, so here's a runway here. I'm coming in at 800 feet, 200 knots. Here we are decelerating now, coming through 165 knots already, and 52 nacelle. We're coming down
RPM, RPM.
Now we're in a hover on the same runway within, I think this is a 4,000 foot runway, so within 4,000 feet, I decelerated from a pretty aggressive airplane profile in excess of 200 knots to a hover and a landing within 4,000 feet, which is pretty impressive.
Next, 40 years trying to solve the problems of tilt rotor technology. The idea of tilting wings and rotors began when designers first understood that helicopters would never fly as fast as fixed-wing aircraft. Boeing's tilt-rotor specialist, Gregory McAdams.
Early in the development of rotorcraft, the military, both the Army and the Marine Corps, realized that vertical lift machines gave them a great advantage for mobility on the battlefield. After the Second World War, there was a surge of helicopter development. And in the process of that, the developers realized that the helicopter had a limitation as far as forward airspeed. There was a physical barrier that they could not get through. So they were limited in forward airspeed by the nature of the beast. And that's when people started to get interested in what is known as a vector thrust machine. Both Bell and Boeing had done extensive research in things that tilt. And in the 50s, Boeing was concentrating on a tilt wing, where the entire wing tilted. The disadvantage with a tilt wing is the transition corridor that is the area from when you're in a helicopter mode to when you're in an airplane mode, is very narrow. It doesn't give a pilot a lot of flexibility. It's not an easy thing to do to convert a tilt wing.
The tilting wing was the problem with the tilt wing. Trying to maneuver in a hover, a pilot had to fight against the wing's massive drag.
That big wing is just a big barn door there.
Bell and Boeing were not alone in exploring the possibilities of tilt-wing aircraft, or converter planes, as they were known. In Montreal, Canadair designed and built the CL-84 Dynavert. The Canadian military financed the program. It practiced takeoffs and landings on U.S. aircraft carriers, and it was equipped with a minigun. The first known tilt rotor was the product of a genius Philadelphia pilot inventor named Bob Licton. His experimental aircraft was the 1G.
He flew it in the early 50s, and he had about 25 hours on it, but never converted it to airplane mode. Unfortunately, it crashed in the Delaware River because of a mechanical failure. He then went on to develop what was known as the GR2, a more sophisticated version of this concept. This was in the mid-50s, and Licton decided to go with Bell because of his fascination with the tilt rotor concept. And working for Bell, he designed, developed, and built the first successful tilt rotor, the XB-3. It was done under an Army-NASA contract, and it first flew in 1955, and it first converted in 1958. Successful conversion to the airplane mode.
Licton's XB-3 was a very unusual aircraft. Its single engine was mounted in mid-fuselage and surrounded by a large air scoop. Drive shafts buried in the wings transferred power to the movable rotors at the wingtips.
There were several of them built. They were used for research and development purposes for the next 5 or 6 years. And then in the 60s, because of the distraction with the war, there was very little research and development done on tilt rotors throughout the 60s.
Canadair in Montreal persisted in its tilt-wing program, although 2 of the 4 aircraft built crashed. In 1972, a Dynavert was flown to the U.S. to strut its stuff in front of the Pentagon in hope the Americans would buy it. The demonstration was impressive, but it was no sale. The tilt wing was a technological dead end.
There was a competition run by NASA, the U.S. Army, and the Navy jointly to develop a prototype tilt rotor. Bell won that contract and developed the XB-15.
The XB-15 set the pattern for all tilt rotor aircraft. With new materials and construction methods, wings were built strong enough to carry the engine nacelles at the wingtips.
It was a small tilt rotor, about 12,000 pounds. It was strictly a research vehicle. It first flew successfully in 1978 and converted to airplane mode.
Gregory McAdams says the XB-15 conclusively demonstrated the advantages of tilt rotor over tilt wing.
Tilt rotors have a very wide transition corridor. The pilot has a lot of flexibility going from helicopter to airplane mode relative to stalling out the wing or remaining in a partial conversion attitude. They're easy to fly, very easy to fly.
When the U.S. began to develop the Osprey, all 4 American services wanted a piece of it. The cost, well over $5 billion in development alone, has been discouraging to some Pentagon planners.
Marines were the catalyst, but when the program started, it was not a Marine-only program. Right from the beginning, it was a joint services program with the Army, Navy, Air Force, and the Marine Corps, all documenting requirements for this aircraft. The Army dropped out in about 1988 for financial reasons. The Air Force, of course, is still in the program. The aircraft that will be used by the Special Operations Command are purchased by the U.S. Air Force. The Air Force had an original requirement back in 1982 for using the aircraft for combat search and rescue. The Navy has a requirement for combat search and rescue as well as fleet logistics support and carrying their special warfare people, their SEALs, in and out of combat areas.
Ospreys have already made many landings and takeoffs on the Navy's fleet carriers and the Marines' assault ships, and their needs have driven the design. The military has identified 35 ways of using this versatile aircraft. McAdams says the Coast Guard is interested in the Osprey's search and rescue potential.
V-22 has twice the speed, 5 times the range of a conventional helicopter. That will allow them to patrol or search larger areas off the coast. And the V-22 can hover and actually pick up the survivors.
Bell intends launching a civilian tiltrotor geared to the intercity and executive aircraft market, based on its XV-15 experimental prototype, which is much smaller than the V-22 Osprey. Orders are pouring in. Bell Textron's Bob Carisse.
The civil application for a tiltrotor aircraft has long been envisioned by the companies as the logical evolution of this rotorcraft. Typically, a new technology has to be proven with a military platform first. Once you've gotten past the cost and safety issues typically associated with a new technology, then it'll migrate to the commercial world. The V-22 is actually a third-generation tiltrotor aircraft, and it has matured to the point now that the company feels that it can step out with a civil version of a tiltrotor aircraft. I think it's the logical evolution of rotorcraft. It will not replace all helicopters. It will not replace all turboprops, but it has its place in the aviation world, and I think that once people see it fly, it sells itself. The potential for the technology is tremendous.
In service with the Marines, the Osprey will replace the old CH-46, the Corps' medium-lift troop-carrying helicopter. The CH-46 is an ancient machine in use since the 1960s.
The things that make it better than what we have now, first of all, the 46 is over 30 years old now. And just aside from the age of that platform, this one provides a lot more technology as far as avionics, navigation, communication equipment, and we can reach out and go a longer distance than we could in the 46.
Troop-carrying aircraft like the Osprey are vulnerable and require an escort of fighter aircraft. With the Marine Corps, that escort will be the Harrier jet, another technological marvel that, like the Osprey, utilizes vectored thrust.
Currently, the Marine Corps has both fixed-wing and helicopters. And out aboard our amphibious ships now, we have the AV-8B, the Harrier, which, of course, comes off the decks, and it's a high-speed airplane. It's a tactical jet. That has to be the kind of escort that will go with the V-22.
With the Osprey, the United States has an insurmountable lead in tilt-rotor technology. Yet even the U.S. hesitated for decades before tackling this formidable task.
The advantages were obvious. The technical challenges were huge. You're dealing with a lot of aerodynamic characteristics, vibration characteristics of that type of machine that we didn't understand back in the 40s and 50s. No other country has pursued it with the vigor that the United States has. I mentioned the technical challenges we had to overcome to bring a tiltrotor to fruition. Other countries recognized those challenges and considered them too big. The U.S. kept pushing for 40 years and finally has one on the ramp today.
One reason it took so long to develop this tilt-rotor aircraft. Until recently, the materials and building techniques needed simply were not available. It has a higher percentage of composites in its fuselage than any other aircraft. Every single part of the Osprey, every curve and line, has been reduced to the digital language of the computer. Subcontractors across the U.S. patch into a massive central database to fabricate its parts. The Osprey's composite Kevlar graphite skin is laid by a computer-controlled robot, precisely 1/8 of an inch thick. It's lighter and stronger than aluminum. Software guides the robot around planes and curves and builds up thicknesses where reinforcement is called for. Lasers line up parts and guide drills. The tolerances are those of a quality Swiss watch. The fuselage is shipped to Bell's assembly plant at Fort Worth, Texas, where wings and engines are installed. Boeing's assembly manager, Don Hicks.
As far as production programs go, the V-22 is one of the few completely digitally designed production aircraft on the market today. And our splice position, for example, is where we can get that splice within about 12 thousandths of an inch or 14 thousandths of an inch, and that's from nose to tail. So it's taking aircraft manufacturing and then putting a little watchmaking into it.
Flight testing at Patuxent constantly reveals the need for minute alterations in the design. That results in long hours of tests in the wind tunnel. Engineer Bill Grau.
Once the aircraft is built and in flight test, typically problems arise in flight tests that need to be solved before the aircraft can move on into production. So the model comes back into the wind tunnel again and is tested to solve those problems.
Telemetry monitors at Patuxent, for example, detected unexpected turbulence swirling off the fuselage, creating aerodynamic havoc over the Osprey's tailplanes. Reworking the body shape at this stage was unthinkable. A simple solution was found in the wind tunnel. Small fins are added to the fuselage. They direct the destructive turbulence away from the tail. To add to their complexity, Ospreys destined for service on carriers have to fold up to reduce their footprint on the deck. It's a big aircraft. The rotors alone have a diameter of 38 feet, and the aircraft has to unfold and be ready to fly in 2 minutes. The twist capsule performs this mechanical magic without the need to disconnect any of the aircraft's many wiring, fuel, and hydraulic systems.
You have to be able to just pull this thing out onto the spot of a ship, unfold the wing and nacelles and prop rotors, start it up and launch without having to go in and break connections and reconnect things in the twist capsule.
The Osprey's giant rotors are powered by Rolls-Royce Allison T400 turboshaft engines through a complicated gear train.
The structure here is what we call the nacelle. It houses the engine primarily, as well as two other gearboxes. There's a tilt-axis gearbox that the whole nacelle actually tilts on from helicopter down to airplane modes, and then there's also a prop rotor gearbox that gears down the turboshaft engine to drive the prop rotor on top.
The engines are coupled by drive shafts, so that if one engine fails, the other continues to drive both rotors. During the flight testing regime, pilots put the aircraft into conventional fixed-wing flight at the slightest indication of trouble.
If we're in a high-risk profile or in a wind-up turn or on a condition that causes a problem that either induces a malfunction on the airplane or sets off an alert in TM, then the TM flight test director down there will radio us and tell us to knock it off and go to a straight and level, basically 185 knot profile.
In emergencies, pilots can't eject like jet pilots, nor can they ride the Osprey to the ground on contra-rotating rotors like a helicopter pilot.
There's no ejection seats in the cockpit, so in an emergency situation where the pilots have to get out as soon as possible, the egress procedure is to blow this window. There's a detonation cord embedded in the glass around the perimeter, and you pull a handle similar to an ejection handle, and it literally blows the glass away from the aircraft. Once the smoke settles or the debris is cleared, then the pilot can get out this way.
The dumpy appearance of the Osprey is partly dictated by her need to carry a big load of fuel to obtain the desired range. She holds the bulk of that fuel in bulging side tanks.
Well, 90% of the fuel is carried on these external, what we call sponson tanks, which start from about here and go forward. Each one of the sponson tanks holds about 1,500 gallons of gas.
Fuel is suction lifted, not pumped, so that if an engine catches fire, its fuel flow stops automatically. A sensitive computer system starts the engines at the flip of a switch, making all of the right settings.
The engines utilize a technology called FADEC, or Full Authority Digital Electronic Control, where the engines are started by a switch inside the cockpit, and all the pilot has to do is select start, and the computer tells the engine, you know, to start turning up, when to introduce fuel and when to introduce ignition to get the light off. If it doesn't like any of the parameters, or the parameters for the start sequence aren't validated by the computer, then it aborts the sequence automatically. And that's an added safety feature, in that it prevents engine damage due to false starts or hot starts, hung starts, overspeed conditions. All those things are controlled internally to the computer, which we refer to as the FADEC.
Like a jet fighter, the Osprey has fly-by-wire controls.
The stick is actually connected to a black box somewhere in the floorboard here, so that when I pull back on the stick, it's not pulling on a cable that's pushing on a control rod that's moving the elevator. It's just going into a computer box, basically, that says, hey, he wants the nose to come up, senses that, feeds it to the flight control computer, and, you know, within the speed of light, sends a signal to an actuator outside the aircraft somewhere and tells it what to do to get the desired effect. What's unique about this aircraft fly-by-wire is that it knows both airplane and helicopter control laws, if you will. So if I was in helicopter mode, hovering like a helicopter, and I wanted to pitch the nose up, I'd pull back on the stick, and the prop rotors would move. Vice, if I was in airplane mode at 200 knots or so, and I pulled back on the stick, obviously I wouldn't want the prop rotors to move. It would sense that and know that the prop rotors are not the appropriate control surface to get the desired effect, and it would make an adjustment on the elevator or the tail.
For night operations, pilots will be equipped with both night vision goggles and FLIR, a system that reveals objects on the ground by minute differences in temperature.
The FLIR is a forward-looking infrared, and it basically senses temperature differentials outside the aircraft. Obviously, every material in the environment radiates heat at a different temperature, so it provides a black and white image inside the aircraft, if you will, of what's going on outside in a video type format. And it's really helpful at night to see the ground and pick out images, houses, buildings, rivers, ponds, bodies of water, things like that. And it's slewed through the navigation system that it'll actually track points on the ground. You could program the lat long of that landmark. It would slew itself to that landmark or that geographic location and then track it until you actually flew over the top of it.
Most systems on the Osprey are triple redundant, 2 backups for every system, including the vital flight control computers and the aircraft's hydraulics.
Now, if I sustained for some reason, I took a round or a 50 caliber bullet and went through the hydraulic system 3, hydraulic system 1 and 2, they would pick up the load that 3 was carrying immediately. Transparent to me. The only way that I would know that that occurred, I would get an advisory, number 3 hydraulic system fail. And I still have complete control of the aircraft because each one of the actuators is double redundant, and it's being powered by the other 2 hydraulic systems at the moment.
The Osprey rehearses for a combat mission. Next. The Marines alone will acquire more than 300 Ospreys. Marine and other service pilots are now joining test pilots in the cockpit. flying combat-like missions, acquiring the skills needed to take the Osprey into battle.
During the typical engineering test, it's normally just a pilot and a co-pilot. We don't take a crew chief or anyone else in the back just because of the risk involved. And it's usually divided fairly in the cockpit between the pilot and the co-pilot. The non-flying pilot will normally keep track of the test and the data points that we've gotten and which ones we need to get, as well as the test director down in TM.
Taxi information, Lima, takeoff. We'll be departing VFR as filed to Pax River to the northwest.
What we're trying to do is we're trying to develop and rehearse what's going to happen for operational tests that's going to be coming up here in a couple months. Because we don't want the operational pilots to do something that hasn't been experienced by test pilots who have a little more experience in trying to ring out the airplane. And we're going to try to get some time before sunset in low light condition, like in what we call pinky time. But yet it's a rehearsal for later on for doing flight at night with night vision goggles.
On this flight, Chris Seymour will take the Osprey far beyond the range of the telemetry engineers and their monitoring equipment.
Well, they will be monitoring the aircraft, but not real time. There'll be a tape running on the instrumentation package in the back of the aircraft throughout the duration of the flight. And when we get back, they'll download that tape and review it. They can only see what's happening within probably 5 miles of the airfield. After we depart that area and get out into the restricted area where we do most of the testing, it's up to the chase aircraft to keep an eye on the airplane. If he sees something from the chase aircraft, then he'll call us on the radio or the test director and let him know what he's seeing. There's several ways that we take off, and one of them is what we call a short takeoff, a stow. We typically stow off at about 60 degrees with the nacelle rotated down to approximately 60 degrees. You add power and you just start to roll down the runway. Then once you have airspeed going across the wing and it starts creating lift, it lifts off the ground pretty rapidly. It'll stow off within the length of its own fuselage. It's a pretty efficient way of getting it off the ground. Tonight is what I refer to as an OT pilot training flight, specifically just to train the operational test pilots who are going to be taking the aircraft next year.
In the future, Air Force Lieutenant Colonel Jim Schaefer could find himself flying into enemy territory to pick up a downed pilot. He's close to qualifying.
What are you looking for, sir? 30 hours?
I'm looking for 24 hours on this flight, and then I got 6 to go for 30 before I can be a hack. Yeah, I feel a lot more comfortable with the button pushing. I've always been comfortable flying it. This is one of the easiest airplanes I've ever touched to fly.
The day tactics portion basically is going to be a 200 level tactics hop. It's part of the syllabus that we created here to qualify them in the aircraft. And basically what we did was we built a simulated or a notional combat scenario along a route of flight between here and West Virginia, Morgantown, West Virginia, approximately 220 miles away.
You already dropped your TOT? Negative. That's coming up next. That's 1 hour after takeoff. I put a 2320 TOT in there. I don't know what this ditch map is doing, but it's not giving me any reliable nav information. He's moving it. How about you, we try the flight director? Yeah, it is. I'll use the heading. Okay. Oh, never mind. I know what I did to you. Stand by.
Waypoints have been fed into the computer so Schaefer can avoid ground threats. The waypoints are all scrambled.
What is that? Drop the thread in there. I did drop it in there. Stepping the map out, see what it is. Whoa. I did put that in there. I did not put that in there. You sure you didn't do it like inadvertently when you were... Positive. Wonder if that happened when we had the cold start. Or that was already loaded. Shouldn't have been loaded.
We did have a problem with the aircraft right after takeoff. There was a small glitch that he was able to deal with. Basically what happened was he lost all of the data points or the waypoints that he put in for the route, and he had to in flight, which was a good training point for him. He had to manually go back in and re-input all the information that he had put in during the pre-flight.
A sensor detects a ground threat, an unknown radar locking on. Schaefer must decide between avoiding it or reaching his target on time.
Well, what do you think? You want to circumnavigate this threat that popped up here and continue on our route? Maybe change our flight plan or something to avoid this thing? Yeah, I don't want to circumnavigate because we're pushing sunset already. Now, we will circumnavigate that much. Exercise the flare on the next waypoint, see if we can track the next waypoint. Tell you what, I'll do better than that. I'll exercise the flare on that threat, see if we can't see what it is. Damn cool. Okay, it's looking. Okay, little airport, 2 miles. Looks like it's up on top of this ridge line here.
Okay, we're going to have to bump it up to 200 now to make our TOT. Let's just try the backside frequency, 249.65.
Osprey 09er flight, Morgantown Tower.
Osprey 09 flight to V-22 with a King Air. We're working...
In wartime, seconds count. TOT, time on target, can be crucial. Schaefer must land at the set time after a 200-mile flight.
Okay, crew, brief us on what you want to do here. Okay, once I hit the turn, we'll do a normal approach to a no-hover landing on the runway. 17 onto the runway is my target.
A small airport at Morgantown, West Virginia, becomes a stand-in for a wartime landing zone.
Well, we had a time of arrival that he had to make at a landing at Morgantown Airport within plus or minus 30 seconds, and he was well within that criteria.
Great. Osprey 09 approved as requested, cleared for takeoff, wind 220 at 7.
Osprey 09. You want to set up the TOT back to the house? Okay, I'm working it. So what were we, 40 seconds early on our TOT at Morgantown? 55 seconds early? Yeah, something like that. That was a pretty aggressive transition, though. It was almost
I did a The Osprey program, not surprisingly given the revolutionary nature of the aircraft, has been plagued with problems. This flight, there's a loose panel on an engine nacelle.
It looks like we got a panel coming up on the right nacelle. I hate to tell you that, Major Seymour.
I see that.
And it wasn't like that 5 minutes ago when I looked outside. We're going to do a run-on landing just to be sure. I think when it goes to the vertical and the airflow against it, it'll keep it, hopefully it'll keep it from popping open. Nacelles and airspeed to go. Up to 100 feet, 84 knots. Yeah, landing nacelles, 10 knots to go. How's our panel look? The flight plan, we cut the corner. Yeah. For a tactical scenario. What was the tactical scenario? Battle damage, that's what it was. There you go. That's right.
Osprey 9, Patuxent ground, taxi to your line, cross runway 2.
Osprey 9, roger.
From my perspective as a Marine Corps major, I'm involved in this for the sole purpose of delivering a good product to the Marine Corps, and that something is not overlooked for an engineering issue, more from a tactical issue. And in a perfect world, what we'd like to have is a reliable aircraft that we can take to the field, we can get it dirty, we can land it in unimproved zones, we can carry the Marines that we need to carry, and we can go the distance that we need to go. And I think essentially we're going to get that out of this aircraft. It's going to take some adjustment on the Marine Corps side, and it's going to take some adjustment on the piloting side. The helicopter community in general is going to have to adjust the way they think about employing an aircraft. You'll be able to go twice as fast, twice as far, and twice as high.
We are all going to benefit, but we look at the Marine on the ground as being the focal point of what we're in support of. We are a air-ground team. The Osprey is going to bring to that young Marine, who we will eventually put someplace on a battlefield, the ability to get there more safely because we can circumnavigate the dangers en route. It will give them the opportunity, if he needs to relocate on that battlefield, to do so much more quickly. And it will give him the protection en route that a current family of helicopters cannot. The Osprey will let us do all of those things, and then let us go to distances and with speeds that we currently cannot do in a helicopter. And, we're very excited about that.